Hi everybody, welcome back to the Professor's Du Bois channel. I'm Professor Victoria here with Professor Corey, and today we're going to be talking about covalent compounds and how to name them. You ready to get started?
We better get started.
All right, let's do it. You ready? Let's do it. All right, so we're going to be talking about covalent compounds. You want to get started?
Covalent compounds have non-metal to non-metal bonds. So what that means is covalent compounds are made up of non-metals. And you remember before on the periodic table that the non-metals they're kind of mostly on the right-hand side, certainly on the upper right. And we have the exception there, hydrogen, which is over at the left. That's considered a non-metal. So when I look at a compound, I often look at the elements that are involved and determine if there's any metals there. If they're all non-metals, these are called covalent compounds. Now there's a couple ways they can bond together. These covalent refers to the type of bonding. It's a covalent bond in which electrons are shared, and we'll get into super detail when we get into bonding. But one type just makes small units, like a water molecule, for instance, H2O. We've got two hydrogens, one oxygen, all nonmetals. That's covalent. But water molecules exist as just each molecule is just two hydrogens and one oxygen. Now, there are a special type, not as many, not as prevalent, but they're called network covalent compounds. So covalent meaning all nonmetals, and the network means that the bonding forms like a three-dimensional network. And I like to think of it as a crystal lattice, which sounds really fancy. But imagine like a three-dimensional bonding. And this is what's making diamonds so strong, is it's the bonding that goes on. It's like a never-ending bonded all carbon. Or another example is our silicon dioxide, which is sand, right? It's just sand. Also very hard crystalline material, but that's made up of silicon and oxygen, which are both nonmetals, and that means that that's a covalent compound.
So a molecule is a discrete entity, one oxygen, two hydrogens. Example here's a sugar molecule over here, but a network covalent can grow in all directions indefinitely. Chemists use formulas to represent compounds and substances, and they are broken down into different types of formulas. One of them is a molecular formula, and a molecular formula is only good for telling you how many atoms of each type of element there are. Doesn't do anything about structure, just how much of each are there. For example, we have H2O2, that's peroxide. So we have two hydrogen and two oxygens. We don't know how they're bonded together, but that's the molecular formula. This is a sugar molecule, C6H12O6. So that's molecular formula. Empirical formulas are the smallest whole number ratio of those elements. So the empirical formula for peroxide is just HO. And the way that we got that is we divided by the greatest common multiple. So since both could be divided by 2, if we did divide them by 2, we would get the empirical formula.
It's worth mentioning that we don't write ones for subscripts. So if you just see an H with no subscript, that means there's one hydrogen.
Good tip.
Pro tip.
Pro tip from the Du Boises.
So different types of formulas. We have our molecular formula, which tells us the atoms that are there and the relative amounts, but it doesn't really tell us much about the chemical structure. So a structural formula, the second one down, will show us how this is kind of laid out. So we can see here that our carbon has 3 hydrogens and an oxygen attached to it. And then there's a hydrogen attached to the oxygen on the right. Now, you might be able to get that from the molecular formula, but you wouldn't know for sure. You wouldn't know for sure. Now, this structural formula is really great, but it's really hard to type, right? So there's a condensed structural, and this is where we kind of work left to right, and we write the formula in such a manner that you can more easily create a structural formula with it. So this CH3 is telling me I've got 3 hydrogens bonded to my carbon. Then there's an oxygen, and then there's another hydrogen. So from that condensed structural, I can write out the structural formula. But one thing to realize is that this is just 2 dimensions, and in the real world, these molecules they're 3-dimensional. So you'll see we've got 3 different ways that we can represent the 3-dimensional nature of a formula. One being the wedge and dash, where the wedge and dash represent that they're going either into the plane of the paper or out of the plane of the paper, with the regular bonds just being in
the plane.
In the plane.
Yeah.
The ball and stick model you'll see in computers and stuff that's really nice. You can usually rotate these around. And lastly is the space filling model, which is probably the most accurate representation of the actual molecule.
Oh, naming. So you're going to need to be able to name a compound from its formula or give its formula from its name. So the first type of naming that we're going to go into is naming molecular compounds or things that are covalently bonded to each other. And the only thing that you're going to be we're going to go through 3 different types of naming conventions that you're going to have to learn, but you're only going to have to learn binary nonmetal compounds. So the 2 nonmetal elements, C6H12O6, we could say that's sugar. You're not going to have to do the chemical nomenclature for that, but just the binary nonmetal compounds like this, HCl, NO. So there's 2 different elements because we know that because there's 2 capital letters. And when we have those, you're going to have to be able to name them. When you write a formula, you would write these elements as if you were reading them from left to right on the periodic table, or in increasing group number, if you had to put this together as a formula.
And notice too, I always check, are these nonmetals? So I look at HCl and I see hydrogen is a nonmetal, chlorine is a nonmetal. Okay. We're going to have to use a set of prefixes, and they're listed right here. I would probably memorize them. This will save time. You can have them handy. But these prefixes are going to tell us how many of each of the elements there are. Now, there's this one funny catch when we name these binary, meaning 2 molecular compounds, so 2 nonmetals. And the catch is, if the first element if there's only one of them, we don't use mono. Otherwise, we use the prefix to represent the number. And another thing that's a little bit funny is we change the ending or the suffix of the second element to IDE. Ide. I like to emphasize it and be like IED. So our first example, we've got 2 sulfurs. So I go to my prefix, it's di. So I'm just going to say disulfur. The first one, I use the whole first name. And then I've got 10 fluorines. So I go to my prefixes, that's deca. And then I've got fluorine. I'm going to drop the INE and add IDE. So this would be disulfur decafluoride.
The second one has just 1 nitrogen, so I'm not going to use mono, just nitrogen. Then I have 2 oxygens, so I need di, and then I change the end of oxygen to IDE, so nitrogen dioxide. And similarly, we only have 1 sulfur, so sulfur, 6 fluorines, hexafluoride, or fluoride.
There you go.
Oh.
You'll see a lot of historical names or common names. So the first example here is N2H4. So this we would name this as dinitrogen tetrahydride. But there is a common name or a historic name is hydrazine for N2H4. We don't expect you to know these historical names except for 2. We want you to know that H2O is water, or you could say dihydrogen monoxide, and the other one is ammonia. We'd like you to know that ammonia is NH3, and that would be nitrogen. I don't use the mono because it's the first one, so it's just nitrogen trihydride.
And The cartoon is talking about laughing gas, nitrous oxide laughing gas. They used to have laughing gas theater back in the day. Can you imagine? Inorganic acids. Okay, inorganic meaning not containing carbon. These acids will produce an H plus in water or a hydrogen ion. The formula often starts with an H, not always. But they are named just like our binary molecular compounds that we just taught you how to name without the prefixes. So HCl can be called hydrogen chloride, H2S, even though there's two hydrogens, still just hydrogen sulfide. There are common names to inorganic acids that you will probably get very familiar with as we go through the semester: hydrochloric acid, nitric acid, sulfuric acid, and so on. Oxoacids also contain oxygen, and they use prefixes like per, hypo, and some suffixes like ous, us. And all of these depend on the number of oxygen atoms, and we have some examples below.
Another class of compounds that you might see are what we call alkanes, and these are organic compounds, and they're all single bonds. That alkane means that every bond is going to be a single bond. If you're not sure what a single bond is, don't worry about that right now. It's just one little dash going between each of the elements that's representing the bond. Remember, these are covalent bonds, so there's a sharing of electrons going on here, and we're going to get into bonding if you're unsure. But just to make matters more complicated, we have a different set of prefixes for the alkanes, and they're listed over here on the right. And the way we do name these simple alkanes is we count the number of carbons. So if in the first example, I've got one carbon, and it's just singly bonded to hydrogen, so I go to my prefix, and it's a methyl. One carbon is considered a methyl, and I'm going to drop the suffix on that and add ane. So all the alkanes end in ane. So 2 carbons, the prefix is ethyl, so we call this ethane. 3 carbons, propane from propyl.
All right, so we want to give you some practice. I'd like you to pause the video and try to name these given the directions that we just provided in this lecture. So pause the video and give it a try. We'll give you the answers in just a second. There's your answers. Hopefully you did well. Give you a moment to jot those down.
All right, thanks for watching, everybody. We hope you found this video useful. I know it's a lot of information, but if you do practice this, you'll get the hang of it certainly very quickly. And stay tuned, because I tell you what, we're about ready to record another video on a different group of compounds called Ionic Compounds and how to name these compounds. So thanks for watching, and we'll see you next time.
Bye-bye.